Howdy, welcome to the Arrow 220 video lecture series. In today's episode, we're going to be covering the Regula Falsi method. It's a root solving method which takes elements from the secant method and the bisection method. So, like the secant method, we take 2 points on the curve and we draw a line between them to do kind of a linear approximation of our curve. But like the bisection method, those 2 points evaluated at A and B need to bracket our solution. So the interval defined by A and B needs to contain our solution. Now, let's go ahead and do a quick example of just the method being used. So let's go ahead and define how to use Regula Falsi. So here we're going to draw our axes, and I'm going to go ahead and borrow this diagram from the slides. So I'm going to draw something similar. Here is a curve. Here's where the actual root is. Let's go ahead and define the interval to be from A to B. And this is where we're going to evaluate our function on the line. So that's f of A, which I will denote f sub A. And here we have f sub B. We're going to connect the line, or we're going to connect the points FA and FB. And that's where that line intersects the x-axis is where we're going to put our Regula Falsi point. This is x, R, F, P, Regula Falsi point. Now, we're going to evaluate our function at that Regula Falsi point. So drop that line there. This is F sub R, F, P. And now we're going to do a sign check, similar to the sign check that we did in bisection. We're going to see if F sub R, F, P is the same sign as F sub B or F sub A. So is FRFP, sine of FRFP equal to sine of A? If that occurs, then XRFP replaces A. XRFP. In the alternative, B is equal to XRFP. And so looking at our equation, we can see that the sign of F sub RFP is equal to the sign of F sub A, which means that A is going to be updated. And now we're going to draw, A is going to be updated and FRFP is going to become F sub A. And so now we're going to draw a new line from FA to the same FB. It's not a very good line. And the process is going to repeat itself. There's a new Regula Falsi point. I'm going to draw it on the line, and so on. We're going to iterate while this is greater than some error tolerance. Once you drop below that error tolerance, you're going to cut your iteration. There are other terminating conditions that we can use to end iteration, and we'll take a look at those at the end of the video. But right now, let's go ahead and review when Regula Falsi works. So, as we said in the beginning, A and B need to bracket your root, which means that the sign of F sub A and the sign of F sub B have to be opposite. Second of all, the function needs to be continuous in this interval. Third, and finally, we can't find a tangential root. So if this curve were to hit the x-axis and come back up, we wouldn't be able to use this method to solve for that root. Even though A and B would be bracketing the solution, A and B wouldn't be opposite signs, so the method would fall apart. Now, let's go ahead and derive the method. How are we actually going to calculate what XRFP is? And I'm going to draw a new picture to help us do that. Here's our curve. Here is the A, B, F sub B, F sub A, and we're going to, let's say, connect these guys with a straight line, roughly a straight line, and here is XRFP at 0, at y equal to 0. So we can define the slope of this line by just doing the rise over the run. So F sub B minus F sub A all over B minus A is the slope of that line, but it's a straight line. So that's also the same slope as 0 minus F of A, F sub A, divided by XRFP minus F sub A. Now, for simplicity's sake, let's just call this X. We can rearrange this now to solve for X, just cross multiply. So we have X minus, wait, there's a mistake here. This is not F sub A, this is just A, okay. X minus A is equal to negative F A times B minus A all over F sub B minus F sub A. Bring A to the other side, and we have that X is equal to A minus FA times B minus A all over FB minus FA. So this is the X at the Regula Falsi point. That concludes the derivation of the formula that we need to use at every step of the Regula Falsi iteration method. And as we can see, look at here at the slides, it's the same formula as what I just derived. Okay, now let's take a look at an example of where we use Regula Falsi to find the roots of an equation. Here I have the function plotted for the equation shown in the slides up top. So this is f of x equal to x cubed minus 2x minus 3. And I'm told here that we're working on the interval 0 to 2. So let's first of all take a look at our plot. Here is 2, here is 0, and it just brackets our solution, which is going to be somewhere here. But in order to verify without a plot that this will bracket our solution, let's go ahead and plug 0 in and also plug 2 into our function. F of 0 is equal to negative 3, and f of 2 is equal to 8 minus 4 minus 3, which is equal to 1. F of 0 times f of 2 is a negative number. Therefore, we bracket the root. So our interval is good. We can use it. Let's go ahead and start the Regula Falsi process. The formula for the RFP point, or for the Regula Falsi point, is A minus f of A times B minus A all over FB minus FA. And that equals 0 minus f of 0 times 2 minus 0 over f of 2 minus f of 0, which equals, this is negative 3, this is 1, this is also negative 3. Now, there's a lot of negative signs, so we have to be careful. Negative 3 times 2 all over 1 minus negative 3, 1 plus 3. 1 plus 3. So we have 6/4 or 3/2. This is x sub r of p. This is our Regula Falsi point. Now we need to evaluate our function there. So f at x r of p is equal to f of 3/2, which equals -21 over 8. And I'm just grabbing that from the slides, which is a negative number. So the sign, of f x r f p equals the sign of f sub a. Since we concluded that f sub a, which is f0, is negative. Therefore, x r of p becomes our new a. So our new bracket is now -21/8 and 2. This is a, this is b. B does not change. So now we go ahead and we repeat the process one more time. X r of p equals a minus f of a times b minus a all over b minus f of a, which equals 3/2 minus f 3/2 times 2 minus 3/2 all over f of 2 minus f of 3/2. And I'm going to skip through all the math, but that ends up equaling 54 over 29, which is our new x r of p point. If we evaluate our function there, x r of p, then this is f of 54 over 29, and that equals -0.2678. So again, we update a. A equals x r f p. And you continue doing this over and over and over again until, again, f of x r f p at some point is going to drop below your error criteria, your error tolerance. And so when that happens, you're done. Now, as I mentioned before, that's not the only stopping criteria. There are some others that we can take a look at. So other than just looking at the distance of your function from 0, you can also use a terminating condition where you just count the number of iterations, where you just stop the process after a certain number of iterations, because you think that if you haven't been able to do it in, let's say, 30 steps, then that means something else might be wrong. Maybe there's a problem in your code, maybe the function isn't defined properly, but for whatever reason, your code hasn't done what you expected it to do in the number of steps that you think it should take, so you're going to end it there. Should have been done by now, but it isn't. The other kind of error that you can talk about is the standard Cauchy error. And this one isn't defined by how far you are from your x-axis. Instead, and that's written right here, instead, you look at the change. So I'm defining standard Cauchy error. You look at the change in the x coordinate for the x r f p point. So again, this is your curve, and initially you're going to have some point here, and then you're going to drop this line and have a new point here. And you can see that with each iteration, apologize for the last one, with each step, you're taking a smaller and smaller step. XRFP changes by a smaller and smaller amount after every single iteration. And so you can define a minimal step size where if XRFP doesn't shift by at least a certain amount, you can assume that your iteration is complete, because you know that basically as this function converges, eventually each step, each increment of XRFP is going to be so tiny that you know that you could keep running your method over and over again, but your estimate isn't going to significantly change. Even if your root solving method hasn't converged onto the right solution, it has converged to a solution. And it's not going to converge onto anything else, regardless of how much longer you run it. So you might as well stop. Because with each step, with each iteration, you're taking a smaller and smaller step. So if you're not going to converge to it now, you're not going to converge to it later either. So you might as well stop. And with that, I'm going to end with Regula Falsi. In the next episode, I'm going to talk about the fixed point iteration method. Now, there are other methods for terminating your iter. Last night. There are other criteria for terminating your iteration. However, there are other criteria. There are other criteria for terminating your iteration. There are other conditions for terminating the iteration. There are other terminating conditions for ending. There are other terminating conditions for ending the iteration. However,